All right, well, we'll get started. We'll get started with the next session. So there are two talks and then a discussion session. The first talk will be by Atri, and it's on the mystery of black hole birth and natal kicks.
Okay, I guess I can start.
Yep.
Yeah, perfect. Hello, everyone. For the past 2 days, 3 days now, we've been discussing about what all we know and don't know about these black hole binary systems we see in our galaxy and beyond. In this talk, I'll be discussing about the existence of the root of all our problems and how it actually, the origin of black hole X-ray binaries by focusing on how black holes are born. I'll be discussing it from the perspective of natal kicks. As the word suggests, natal kicks has something to do with black hole birth. Theoretically speaking, I think we can all agree that a stellar mass black hole is formed when a massive star dies. Now, this death can happen in two ways. One is accompanied by a supernova explosion. So, a massive star runs out of fuel, collapses onto itself, throws away its outer layers in this supernova explosion, leaving behind a protoneutron star. Now, further fallback of matter onto this protoneutron star can give rise to a black hole. The other way in which a black hole is probably formed is by a direct collapse. So the same thing, massive star runs out of fuel, collapses, but in this case, there's a failed supernova, which means the star just vanishes without any signature. Now, this sort of mechanism is known to happen for supermassive black holes, but for stellar mass black holes, there's just one particular strong candidate, which you can see on the right figure. These were two HST images taken 7 years apart, and this is one strong candidate that is supposed to be a black hole formation. So there's basically these two birth pathways, a supernova explosion or a direct collapse for a stellar mass black hole. From simulations point of view, there are a few work has already been done. One such example is the work done on supernova 1987A by Subbot et al. In 2016. So the y-axis signifies different models that they tried to use to try and estimate what kind of a progenitor made a compact object and also the supernova. As you can see, depending on different models, the colors signify what kind of compact object was formed with what pathway. The result sort of is all over the place. So this does not really give us a direct idea of what happened. Was there a black hole formation with supernova explosion, direct collapse, a neutron star formation with a supernova explosion? So simulations seem kind of inhibiting in that sense. The other way to find out how black holes are born could probably be if we have some amazing direct observations. Like, for example, in this case, this is SS433. It's a bright microquasar sitting right in the middle of a nebula, which leaves less doubt for us to say, oh, this black hole was probably born with the supernova explosion, and now it's blowing away all these different kind of blobs in this nebula now. The other way is, of course, a direct candidate like this. Now, because in terms of direct observations, we can literally count on our fingers how many such candidates we have, this does not seem a great way to make progress to understand how stellar mass black holes are formed. So we've been saying this again and again in the past, like in this workshop, that maybe the next step is combining some observations and simulations, and that may lead us to the answer. So what I mean here is we have all these at least 70 low mass X-ray binary and high mass X-ray binary systems combined in our galaxy that we know of. So we can observe them in the current epoch, find some simulations that can take us back to the way that they were born. One such property that might help us link the systems that we see in the current epoch to the way they were born are natal kicks. So in a stellar binary system, when one of the objects goes off in a supernova explosion, there's a lot of mass loss, which results in a sudden shift of the center of mass, and which will result in the binary getting kicked off. And that will give the binary some few tens of kilometers a second recoil kick. Now, if there are additional asymmetries involved with the supernova explosion itself, for example, asymmetries in the mass ejection, or asymmetries in the neutrino emission that is associated with the supernova explosion, as has been suggested by this paper 1984, where they say that 1% asymmetry neutrino emission can actually lead up to 300 kilometers a second of natal cake to the binary system. Or maybe a mechanism called as a tugboat mechanism, wherein the asymmetrical mass ejection kind of gets gravitationally bound to the compact object formed and pulls it in that direction. And that can also lead up to thousands of kilometers per second of natal kicks. Another way is a gravitational wave emission, which can also be in some cases asymmetrical. This particular paper that I've mentioned here does all the heavy lifting for the mathematical work, but even that has been considered a great way to get high natal kicks. Black hole natal kicks were originally, or till now, they've been discussed in form of neutron star natal kicks. So extrapolating from what we know of neutron star velocities, because we've observed so many of them in the sense of pulsars, and extrapolating them to black holes. But clearly there are many, many more mechanisms in place. And so we need to have some more direct information about how these natal kicks are given to black hole systems. In case of supernovae, in case of a direct collapse, you will not see such high recoil velocities because there's no asymmetries involved. There is no sudden loss of mass. And so measuring natal kicks becomes a great tool to trying to differentiate between supernova explosion, where you expect large natal kicks, and direct collapse, where you do not expect large natal kicks. Other than telling us about how a black hole is formed, differentiating between the two birth pathways, natal kicks are also an effective way to try and understand, maybe there is a mass cutoff between how large a star is before it starts to try and do a direct collapse. Most of these systems that we observe today, we try and also get mass estimates. So we'll know how massive a black hole is. We'll know how strong or not strong the kick was. And maybe we can try and find a correlation between these two things. Another important aspect of natal kicks is the fact that it'll try and influence how binary evolves in the, excuse me, try and influence how binary evolves in the future, because a stronger natal kick might end up either extending or shortening the orbital period, the orbital separation. And so getting a handle of that also helps us to understand how the stellar evolution, binary stellar evolution happens. It's also been suggested that natal kicks could be a very strong reason for spin orbit misalignment, because a strong kick to the black hole itself might just end up pushing it out of the angular momentum, orbital angular momentum. And if it doesn't get enough time to tidally become centralized, this spin orbit misalignment later on might give rise to QPOs. Another aspect for natal kicks is retention factors. So decades before, we initially thought that most of the globular clusters that we have cannot host and retain black hole X-ray binaries. But in the last decade, we've had a couple of detections of black hole candidates, which then suggest that there may be some way to possibly host black hole X-ray binaries in globular clusters. Getting a handle of natal kick distributions and then using that to do population synthesis models will help us understand better what is actually happening in these globular clusters, if it's possible to actually retain black hole X-ray binaries in globular clusters, or the candidates that we are detecting are not necessarily black hole candidates. Another direct influence is population synthesis for the number of gravitational wave events we expect. Because if the natal kick distribution, the natal kicks that these black hole systems get, if they are generally just strong, it might end up unbinding binaries. And if there is no binary in existence in the first place, it gets very difficult for the second stellar object to become a black hole, and then the binary to merge. As you can see in the plot on the right, as in when you increase the natal kicks, which is the x-axis, there's a strong decrease in the rate of merger events, which is the y-axis, that we can expect from LIGO. And so having a good handle on what kind of natal kick distribution we expect will help us understand how many of the gravitational wave events we should be expecting going forward. It was discussed very well yesterday about how we're detecting, in LIGO, how we're now detecting these pair instability black holes that are not basically explained by the standard stellar evolution models that we know. And one of the explanations is possibly that two smaller black holes merged and made this heavier black hole, which then merged with a third black hole. Now, if there are strong natal kicks involved in these black hole formations in the first place, it might end up unbinding binaries. And then the probability of detecting such triple heavy pair instability mass gravitational progenitors becomes really, really less. So what I'm trying to point out here is getting a handle on natal kick distributions is not only important to understand how individual black hole X-ray binaries in our galaxy was born, but a population study of all the systems is necessary to try and answer many other questions, and especially related to population synthesis codes. Hopefully I've convinced you that it's important to measure natal kicks. Now let's discuss how these natal kicks can be measured. So measuring natal kicks basically means measuring how fast a system is going at the point of birth of the black hole. To measure how fast any system is going, you need three basic parameters: the proper motion, which is motion of the system in the plane of the sky, the radial velocity, which is the velocity towards or away from the observer, and the distance or the parallax, so how far the system is. Combining these three aspects together, we get what is called three-dimensional space velocity. So you know how fast the system is moving when you're observing it. What we need to do now is take the system back in time, because we need to go back to the time the system was born. So track its galactocentric orbit, basically take it back to the gravitational potential of the galaxy. And at the time of the birth, you get the natal kick. Ideal case scenario. The problem here is for most low mass X-ray binaries, that is the focus of this study, we don't really know what the age of these systems are. So taking it back to the time of birth becomes kind of impossible. The next best thing is assuming, or mostly we know if these systems are not born in globular clusters and kicked into our galaxy, most of them should be born in the galactic plane. So instead of trying to take back the system to the time of birth, we take the galactocentric orbit to say 10 gigayears. And every time it crosses the galactic plane, we note down the velocity. So you let the simulation do its thing, take the orbit back to 10 gigayears, and note down the velocity at every plane crossing, which basically gives you a velocity distribution, which is almost similar to what this the system must have gotten the velocity to go out of the galactic plane. Of course, because these are three different measurements, proper motion, radial velocity, distance, you will have error bars associated with it. So we can't just take one number and run through the simulations. We'll have to do Monte Carlo simulations. So we use distributions for all three inputs, taking care of error bars, letting it run for 5,000 different orbits, and we get kick distributions. So we can run through individual system, and we can run this through so that we get a kick distribution, and getting a measurement for that kick distribution, we can then compare if it's strong enough for a supernova explosion or a direct collapse. Now, the next thing to note is how we're doing these measurements in terms of proper motion, radial velocity, or distance. For radial velocity, we hope and we need that our optical and infrared instruments, as soon as these sources go into outbursts, they measure that and they get the radial velocity of these systems. Of course, it's not that straightforward, but what I'll be focusing on is the proper motion and the parallax measurements of these sources. One instrument that does that is the Gaia satellite. Now, the proper motion of black hole X-ray binaries is a few milliarcseconds a year, so we need precision astrometry. This satellite does astrometry and spectroscopy of a billion sources, continuously scanning the sky, and gets multiple epoch measurements of the stellar sources in the galaxy, stellar sources. Now, these low mass X-ray binaries are transient sources. It's so difficult to catch them and make sure that the Gaia scanning sort of aligns with when these sources are going off. But there's still some measurements that are there for proper motions and parallaxes, depending on how long the outbursts last. We have error bars on these sources as well. Another issue with just relying on Gaia for getting these measurements is the fact that the outburst optical magnitude for black hole X-ray binaries is almost on the limiting edge of what Gaia can do. So parallaxes are not really doing that well with the data releases that we've had with Gaia till now. Another tool or another wavelength which helps us do precision astrometry is the radio wavelength. So you've heard this before and yesterday as well. When a black hole X-ray binary goes into outbursts, there's different stages, and there's particular stages that you can see radio jets in. Soft state, you don't expect any jets. Then there's this intermediate states where the jets are emitted out as blobs. So if you want to do astrometry, find out where the black hole is, you don't want to be tracing these blobby jets. What you want to be tracing is something which is causally connected to the black hole. So we focus only on hard states. So we do astrometry of these sources only when the black hole X-ray binary is in an outburst in a hard state. As I mentioned, we need high precision astrometry. So we need very long baselines. The instruments that I use, or the arrays that I used, are very long baseline arrays. So they have dishes spread across all over the US, the European VLBI network, which has dishes across Europe, a few in China, Russia, and South Africa. Then there's the long baseline array, which is dishes across Australia, one in South Africa, and one in New Zealand. Now that we have our scene set up, we need black hole X-ray binary outburst. We need it to be ideally in a hard state. We need our VLBI array ready, depending on northern hemisphere or southern hemisphere where the source is going off. And then we need to make measurements and get our natal cake distribution. So how that is done, I'm going to use the example of MAXI J1820 to demonstrate that. The number of times MAXI J1820 has been said in the last 3 days is quite funny. So I was just curious to find out how many mentions there are on arXiv. And the past 3 days, there's past 3 years, there's 159 articles of this particular source. So really, really popular. And of course, so as well, because it went into outburst in 2018, beautifully stayed in a hard state for quite some time, went into 2 mini reflares. So there were lots of multi-wavelength campaigns just focused on this source. We also got 8 epochs using VLBA and EVN. On the left plot, you can see the motion of the source in the sky as varying with time. Fitting straight line through those points, you can get the proper motion, so motion in the plane of the sky. What then remains is the parallax signature, which you see on the right panel. The parallax signature that we measured was with a 10 sigma significance, which is only I think the third black hole X-ray binary for such a strong parallax measurement. And now this parallax needs to be converted to distance. I mean, long are the days gone where we can just do one divided by parallax and get the distance. In the past few years, we've been made very aware of the fact and the use of priors and how important that is. I'll be happy to discuss this later, but currently I don't have the time. So I'll just assume that we all know that we have to use prior to convert these parallaxes to nice distance distributions. And we use the distance distribution, we use a proper motion measurement, we use the radial velocity, which our collaborators did successfully obtain with really great precision, accuracy. And we measure the velocity in the current epoch. We do some simulations, which helps us take it back to the gravitational potential and chart out its galactocentric orbit, as can be seen in the plot. Every time the orbit crosses the galactic plane, we note down its velocity. Run this through 5,000 orbits. And what we then get is a kick distribution, which is the distribution you see on the right panel. As you can see, the median of this distribution is almost 120 kilometers per second. To put this into perspective, for massive stars going through our galaxy, just normal dispersion through the galaxy will lead to 50 kilometers per second, up to 50 kilometers per second dispersion. So 120 kilometers per second is really, really high as compared to that, which then suggests that this source probably did get a natal kick at the time of birth, which has sent it flying through the galaxy with such high velocities. And it's probably born with a supernova explosion. We did this analysis for 16 sources. So combining, getting more observations, radio observations for other targets when they went into outbursts, combining archival data, getting some data from Gaia. And we ended up with these distributions for 16 potential kick distributions for 16 sources. Out of these 16 sources, 75% of the sources seem to have been born with strong natal kicks, suggesting supernova explosion birth. As you can see, the last few distributions, they're still quite loosely constrained. And that's because of the problems that I mentioned earlier, which is the parallaxes will have error bars. If the source is not in a strong outburst for a long time, the chance of getting strong constraints gets really reduced. But the good part is that the code takes care of that because we use Monte Carlo simulations and we have error bars that we've taken care of. So at least even if it's loosely constrained, there's still some constraints. Now that individual sources are taken care of, let's try and see what this says about the black hole X-ray binary population at hand.
Picky, I just wanted to say you have about 5 minutes left.
Thank you. In terms of the black hole X-ray binary population, so we combine these 16 distributions that we have. And by Bayesian hierarchical modeling, we try and fit unimodal and bimodal distributions. The choice of bimodal distribution is because if you expect 2 different populations of direct collapse and supernova explosion, you should have 2 different components to the distribution with a low velocity and a high velocity. With the current sample set, a unimodal distribution is preferred, and the median of that unimodal distribution is 107 kilometers per second. What I would like to point out now, this does not mean that there is no direct collapse lower component to this distribution. It's just that we are still in the low sample statistic stage. To put it into more perspective, the unimodal fit, which gives 107 kilometers per second, suggests that most of these systems, if they are born in globular clusters, will get kicked out, because a typical globular cluster escape velocity is just around 50 kilometers per, a few tens of kilometers per second. So you would not expect to find many of these sources in globular clusters. Now, to try and see if there's actually any relation between how strong the kick is and what the black hole mass of the system is, we did try and plot out and do some correlation tests. With the current sample in hand, there is no strong correlation, but as you can see, the scatter is mostly because of large error bars on a lot of masses. Also, quite a few of these are assumed to be at solar mass because we don't know what the mass of these black holes are. So hopefully in the future, if these measurements get better, if some of these sources go into more outbursts, we might be able to improve this plot. And also another way to do that is populate this plot even more by focusing and trying to get as many mass measurements in as a broader of a mass spectrum as possible. So where do we go from here? We have these black hole X-ray binaries going into outbursts. Gaia is going to stop, I think Gaia is going to stop working after a few years, this year actually. So VLBI is probably a very strong tool that we need to continue using in order to estimate proper motion, parallaxes of these sources. And we need to make sure that we have constant working proposals with all the VLBI arrays. 75% of these systems seem to get strong natal kicks. Does that then suggest that the majority of the systems that we have in our galaxy have spin orbit misalignment? Does that mean we should be observing QPOs because of this in almost all the sources? Of course, all of these questions cannot directly be answered by these observations, but using the distributions that we have observationally, they can then feed into the information that is needed to do population synthesis and try and understand the kind of population that would generate in our galaxy of the black hole systems, see how much spin orbit misalignment we should expect. I think we're getting to the point of where we can start to model the history of individual sources back to the time of birth, rather than just having a simple galactocentric orbit taking us back. For example, this work was done for these 3 particular sources, which were very well observed in, I think, the 2000 to 2010 era. And now that we have sources like GX339-4, Maxi J1820, which also have very strong good constraints on a lot of measurements, that can feed us and let us see if there are evolutionary pathways, are just if all these systems can be explained with similar evolutionary pathways, or does it just like get crazy, as was explained by Chris in his talk yesterday, when we start to consider the LIGO sources. We have to start considering using observationally constrained kicks as input for population synthesis codes, which will then help us understand how many of these sources can be retained in globular clusters, what kind of gravitational wave, what's the rate of the gravitational wave sources that we actually expect. And of course, those distributions can be improved once we have better understanding and we have more sample set. So we have to continuously keep increasing the sample set to at least double the current size to improve our natal kick distribution, which will happen if we have better and more coordinated follow-up of these sources. We just cannot afford to let any of these outbursts go to waste. We have to make sure we have all our radio, optical, infrared, and X-ray proposals in place and just ready to observe as soon as any of these sources go off, because they don't really go off that often, which brings me to my final point. We also need more long duration outbursts, a call to the universe to send more long duration outbursts so that we can follow them up more and get our models in place to actually understand how black holes are born. Thank you.
All right, very nice talk. Thank you. That's some great data and an important problem, and there are lots of questions. I see 4 on Zoom right now. Let's go to Javier Garcia.
Hi, thank you. That was a great talk. I was just wondering whether you have any relationship between the natal kicks and the spin of the black hole. Have you thought about that?
Yes. And I mean, I'm pretty sure that there should be a relation between natalkicks and the spin of the black hole, because you expect these systems to be, I'm sorry, I'm getting some feedback. Yeah, you expect these systems to be rotating really fast, becoming binaries. And then after that binary stage, if there's a chaotic kick happening, which is leading to mass loss, and if there's a preferential direction, there might be, and I think there should be a change in the spin of the black hole, which if not given enough time to tidally constrain, it probably lead to spin orbit misalignment even now, even after years of the source actually being formed.
So just to follow up, do you think the black hole can acquire angular momentum through the kick? Will be the better question, I think. Because it's a big question. How do the black holes that we observe in binaries have acquired maximum spin or large spin in some cases?
Yeah, I think that if there is a preferential direction in terms, because asymmetries can lead to some increase or decrease in angular momentum there, so it might lead to some angular momentum being gained by the system as a whole. And I mean, I think the LIGO observations also, a few detections, they did suggest that they were either maximally spinning, which suggested that they do not have enough time to tidally just forgetting the recircularize, I'm forgetting the term, but just tidally become constrained enough to then lose all that angular momentum and become aligned again. That answers the question.
There is a question in the room.
Okay, great. Let's go to the room.
Okay, it's your reporting. Thanks for a great talk. I'm actually interested in MAXI 1820 plus 070 because I have a paper on that appeared on Astropatient Friday. And the estimates for the kick that you have, is it based on the one transition passing through the galaxy or many passing through the galaxy? Because you don't know exactly what point this was born, right?
Yeah, we don't know when it was born. And that's why that's a distribution which makes sure that the system goes through the galaxy as many times as it can based on the current velocity if we just extrapolate it back to 10 GeV.
So this distribution that you show is for many passes?
Yes, this is multiple passes through the galactic plane and also for multiple starting values as well.
Okay, the related question is, of course, if you know the distribution or the velocity that you measure, we probably can predict what misalignment you would expect, right?
Yes, I think, we were discussing this on Slack yesterday as well.
Yeah,
that's where the modeling people, that's where the modeling people come into picture, which I'm not really great at, but would love some ideas if anybody has them. Yeah.
Great, thank you.
Okay, next question, Poshak. And unmute, yeah.
Thank you. Yeah, very short comment and a quick question as well. As far as I'm aware, Gaia will not stop working this year. I believe there is an extension up to 2022 at least, the end, and possibly up to 25 as well. There's enough propellant for it to continue, as far as I'm aware at least. I had a question on your error bars for MAXI 1820. I don't know if you're able to go back to that slide, but I just wanted to understand the deck offset. The error bars seem very small for the EVN, was it EVN or VLBI data, sorry. I was just wondering if that affects the uncertainties.
So you were talking about,
slide 13, I think it was.
So which plot are you talking about here?
The deck offset, the bottom right panel.
Yes.
So the uncertainties there would suggest a very bad fit, but I just wanted to know, if, how you determine the final uncertainties are.
Yeah. So most of the signature for this parallax is in the RA direction. As you can see, most of the points in the deck relation offset, they mostly align with 0. There's this one EVN data point, which I have no idea why it's behaving like that. I have talked to the people who actually got us this data at Jive. Even they are perplexed. They asked me this question, I asked them this question back. We just don't know what's happening, unfortunately.
Okay, thank you. But so just to clarify, do the uncertainties account for this essentially?
Uncertainties in the parallax measurement. Yes. So the uncertainty that you see here of 0.033 account for the systematic uncertainties that you can get based on different calibrators that we use. It accounts for the error bars on individual sources as well. So we did, again, this was Bayesian fitting. So we did consider all possible error bars.
Thank you.
We have a question in the room if you have time.
Okay, 2 more questions. We'll do the room and then Alex Tedorenko, and then we'll move on.
Hi, Piki. Thank you for the great work and great talk. I had a question concerning, so there were low mass X-ray binaries, right? And that's kind of a follow-up question of what Javier asked. In the case of Cygnus X1, we know that the natal kick is very, very low compared to what you measured. So can this difference be purely ascribed to the fact that in Cygnus X1, the mass ratio was closer from 1? I mean, the companion was much more massive than in your low mass X-ray binaries, or could it be partly, I mean, could part of the angular of the natal kick have been converted into somewhat into angular momentum of the black hole?
For Cygnus X1, that was actually one of our test cases because we know so much about that source. We want to make sure our simulations run for that. The motion is not that different from what you would expect just from the peculiar velocity of the source. We already know it's not possibly in a supernova explosion because it hasn't had time to go away from the Cygnus OV3 association as well. So I'm not really sure if, because yeah, so we do suggest it's actually born with a direct collapse. So I don't think it really got a strong natal kick. So yeah, that would not then convert into angular momentum.
Okay, thank you.
Okay, Alex.
Hey, awesome talk. I kind of have more of an observational question. So you're talking about you need to be doing these kind of astrometric observations on like the hard state jets. I'm curious if is it going to be possible to do this on like quiescent systems with next gen instruments like NGVLA?
Yes. The sensitivity promised with NGVLA, if it goes as low as that, because we still don't know how faint these sources are in radio inquiescence because we haven't gone that deep yet. But if we can, then NGVLA over long time period might be able to at least get us proper motions. So that is actually something that I'm looking forward to.
Cool, thanks.
Okay, so let's thank the speaker again.